a small object is placed 30 centimeters in front of a thin lens L1 of focal length 10 centimeters, an image is formed behind the lens. When another lens L2 is placed in the contact with L1, the image formed at infinity. L2 is we have to find the lens type and lens focal length of lens. In the first situation, object is placed 30 centimeters in front of the lens, focal length 10 centimeters. After placing L2 lens, image formed at infinity. It means it should be like this. For the first condition, object distance is 30 centimeters. Then we can obtain an image in this side. We know that we can get the image behind the lens by using convex lens. After placing the second lens, image is formed at infinity. To form the image at infinity, focal length of lens combination should be this value. After placing the second lens, image formed at infinity, it means light rays from this point are moving parallel to the main axis. Then this one should be the focal length of combined lens. Then we can use combined lens formula. 1 over f equals 1 over f1 plus 1 over f2. 1 over lens combination 30, it is a minus value because of convex lens. F1 focal length is given as 10 centimeters. It also minus convex lens. We have to find f2 value. Then I will subject f2. 1 over f2 equals minus 1 over 30 plus 1 over 10. SCM of denominator 30. 30 divided by 31, 1 into minus 1, minus 1. 30 divided by 10, 3, 3 into 1, 3. 1 over f2. Then we can get f2 value should be 15, it is a plus value. Plus value means it should be a concave lens. Focal length 15 and it should be concave. Then answer is 1. When an object is placed on the principal axis of a thin convex lens of focal length f1, it forms a real image at distance v1 with the linear magnification m1. When this lens is replaced by another thin convex lens of focal length f2, they have given f2 is less than f1, being kept at the same position. The new image distance v2 and magnification m2 will satisfy the condition. We can get the equation for the linear magnification. I will use directly 1 over v minus 1 over u equals 1 over lens formula. Then we can consider sign convention. Lens is a convex lens, therefore it should be a minus value. There is a real image. We know that we can obtain a real image by using a convex lens for the object distance it should be greater than f value. F means focal length, and it should be in this size. Object distance is in this size. Then we can get object distance is a plus value, this minus mark is this one. Image should be formed at this size. Therefore, we have to get image distance as minus. Then I will change opposite all marks of terms. Then 1 over v plus 1 over u equals 1 over s. We know that linear magnification means v over u ratio. Then we can multiply all terms by v. V divided by v1 plus v divided by u equals v divided by s. Then we can get this one is the linear magnification m. Then m value is v over s minus 1. Now I will draw the VU curve corresponding to convex lenses. We know that VU curve means image distance versus object distance. It should be like this. Now we have to get VU curve for the real images. Therefore, it should be this side. We have to get this shape. Now we can get when f is decreasing. For the second situation, f2 value is less than f1. Therefore, we can get v2 should be less than v1. v2 should be less than v1. We know that when f value is decreasing, it should be graph should be moved to this side. We can obtain a small image, and when considering magnification, it should be smaller than first condition. Then we can get m2 should be less than m1. Then we can get fourth one is the correct answer. Number 23 is written on a piece of paper placed on the flat horizontal surface of a table. A thin convex lens is held just above the number, and then it is slowly taken vertically upward while looking at the image of the number through it and keeping its optical axis vertical. Which of the following best represents the variation of the size and shape of the image as the lens is gradually moved up from the number 23? We have to use this VU curve. For the initial situation, object distance is less than s. When increasing object distance, we can get that image is magnified. It is a magnified image. It means V value is greater than U value. Then V over U ratio is greater than 1. Therefore, we can move length up to focal length such that we can obtain an uninverted image, and it should be magnified with distance. Magnification is increasing with distance. Therefore, it should be like this. After increasing object distance, after f, we can consider it should be an inverted image. We know that this region after focal length, we can obtain inverted image. Inverted then, when considering corresponding UV values, when increasing U value, V value is decreasing. When increasing U value, V value is decreasing. It means magnification is decreasing with distance. Therefore, it should be first answer. You can obtain, it is like this, inverted and magnified image. Magnification is decreasing, then we can get a small image. Then increasing object distance. Then answer should be 1 for the question. A standard photographic size has a picture size 30 by 40 millimeters. An enlarged image of slide is projected into a screen 4 meters away from the projection lens of a single lens slide projector. If the size of image on the screen is 1.2 meters by 1.6 meters, what should be the focal length of the projection lens? We can get linear magnification. M is V of f minus 1. We have obtained in this question. Then linear magnification should be, I will consider the magnification of 30 millimeters size. Then object height is 30 millimeters. Corresponding image height is 1.2 meters. 1.2 meters. We can convert it to millimeters. 1.2 meters means 120 centimeters. 1200 millimeters. Divide by 30 millimeters. Object height 30, image height 1200 in same unit. Image distance is 4 meters. 4 meters is 400 centimeters. Divide by focal length minus 1. Then we can find the f value. 40 plus 1, 41. Divide by 400. Is 1 over f. Then f value is 400 divided by 41. We know that when dividing 400 by 40, we can obtain, it is as 10. But this value is greater than 41, therefore this answer should be less than 10. We can get approximately 9.8 centimeters. Then answer should be 2. An arrow beam of monochromatic light XY falls on converging lens L as shown in the figure. After refraction through the lens, the beam hits the screen S and makes a light spot. What would be the position of light spot? Then finding the path of light ray, we have to use the light ray passing through the hole, this point, and which is parallel to the given light ray. I will draw the light ray passing the pole and it is parallel to the given light ray. It will not deviate. Then I will draw the focal plane. Focal plane means the plane passing through the focal point. It is like this. Then we can obtain the path of this given ray also should be passing this F point. Then we can get the position of light spot is this one. It should be point D. Then answer is 4. An object is placed in front of a concave lens as shown in the figure. the path of the refracted rays emitted from point A of the object are. In this question, the diagram is not given. I will draw the corresponding diagram. It should be like this. There is a concave lens. This one is the focal point. From A, there are some rays like this. P. Q. R. This passing the pole. S. We know that when getting a parallel ray, it should pass the focal point, this focal point. Then P is correct. Then Q ray, it is moving towards the focal point, like this. And after refraction, it should move parallel to the main axis. It also correct. The path of the ray passing through the hole is not changing. Therefore, R is correct. S is incorrect. We can't get a ray like this. It is moving. It is refracting towards the main axis. We can't get a light ray like this by using concave lens. Then only P, Q and R true. Answer is fourth one. Which one of the following which one of the rays drawn in the figure is not correct? We can consider given rays by using the same method. We can identify when considering the ray E. It is like this. But we know that we can't see the refraction towards the main axis by using concave lenses. Then E is incorrect. Answer is 5. The person takes a picture of a aquatic plant in a container with a thin glass wall using a convex lens. The container is filled with water. Then the film, lens and aquatic plant are positioned as shown in the figure. The clear image of aquatic plant is recorded on the film. Refractive index of water is 4/3. What is the focal length of convex lens? Aquatic plant is at a distance 40 centimeters from this edge. First of all, we have to use N equals real depth divided by apparent depth. Real depth divided by apparent depth. In value is 4/3 for the water. Real depth is 40. Apparent depth we have to find it. I will consider it as x. Then we can get that x is 30 centimeters. Therefore, object distance corresponding to this length should be this 10 length plus apparent depth. It means 30. 10 plus 30 is 40. We have to consider apparent depth, not real depth. Then U value is 40. Image should be formed on the screen, which is spaced 10 centimeters. Therefore, V value is 10. We have to find it. Now we can consider sign convention. U is light rays are moving towards this direction. U is opposite to light phase, it is a plus value. V is same direction, when considering with light phase, it is minus. We have to find x. Now we can use length formula. 1 over V minus 1 over U equals 1 over S. Image distance is minus 10. Object distance 40. We have to find focal length. Then I will consider LCM of denominators 40. 40 divided by 10, 4 into 1, 4 is minus. 40 divided by 41, 1 into 1, 1 minus. 1 over S. Then we can get S value is minus 8 centimeters. Minus means it is a convex lens. Focal length is 8 centimeters. Answer should be 1.